In this video, we'll be discussing the remedial measures in simple linear regression. That is, what approaches can we take to help us out if we find out that our assumptions have been violated? So frankly, we're just going to look at a review of the assumptions very quickly at the beginning here. And then we're going to look at some of the different ways that we can approach things that have been broken. So for instance, if our residuals are showing that we don't have normality, if we don't have constant variance, or if we're having trouble with linearity, what can we then do? What options are available to us to address this? We'll talk about some in this lecture set. There will be others that may have to wait for other courses, more advanced procedures that are typically used in the field, but things that are a bit above our level or outside the scope of this class. We will talk about one of the biggest ones that is most commonly used in the field in this lecture series, though. So regarding the assumptions, recall what the assumptions were. We had that epsilon IID in parentheses 0 sigma squared, and recall that that was the errors are normal, independently distributed, they have a constant variance. Some students sometimes wonder, why don't we check the assumption that the errors have a mean of 0? And that's actually a really good question. The main reason we don't is because our model, just by the definition and by the procedures that we use to create it, guarantee that the errors will have a mean of 0. So it's something that incidentally turns out to always be true just by the procedures that we use. Recall also that we had some things involving model fit. We looked at that linearity, the importance of predictors, making sure we have all the predictors in the model, and then we mentioned that we shouldn't have outliers. So we'll discuss how to approach many of these in this particular lecture. Now for the remedial measures, again, this comes up when things break. And we have kind of three options when our assumptions break. The first option is to ignore the problem. Now, we're not going to talk about this today, but ignoring the problem often leans on the fact that many statistical procedures, the interpretations of p-values and statistical tests, are still valid, even when the assumptions aren't met if there are only slight or minor violations of the assumptions. So you can think that our data aren't perfectly normally distributed, but they're not too far away from normally distributed, and our statistical tests will still have valid interpretations. This is true in many statistical tests. It's true in some cases more than others, and the consideration of robustness of different statistical procedures is the topic of many academic papers and Wikipedia articles and blog posts that you can go and look up. Long story short, it tends to be true if the violations are relatively minor. For many statistical procedures, it tends to not be true if violations are major. Now, there are some conditions under which minor violations are still problematic. These primarily have to do with sample size. So if we have a small sample size, even minor violations may be pretty problematic, though if we have larger sample sizes, they tend not to be. This is especially true in groups, which is not what we deal with in regression, at least yet. We will talk about that later in the course. But on a regression equation, it's a little less important. The second option that we can do, as opposed to just ignoring the problem and going on with business as usual or making a minor note, is to use a more appropriate model. So there are other statistical models that also tend to go beyond the scope of this class. They tend to be much more advanced, more complicated. But there are statistical models that don't make the same assumptions. In fact, we have an entire class called non-parametric statistics where you can learn completely. It's an entire class devoted to statistical models that don't lean on the traditional assumptions that we make in regression and in all of these statistics that are based on the regression model. We'll talk a little more about that too later in this lecture. The last option that you can typically do is look for data transformations. What we're going to end up doing is apply a function, and when I say a function, I mean think of square root or the squared or taking the log of to the data and hope that after we apply the function, when we take a regression of the data, that regression, that the assumptions of that new regression equation will now be met. So this is the third option, and this is what we're going to focus on today, actually, is looking for a transformation of the data. We'll talk with each of the remedial measures, and we'll go through violations and the options for each. There are sometimes some more options that we can use, or some more obvious options we can use, but the primary focus of the fix that we're going to talk about in this lecture set is the transformations. So first thing we should talk about here comes up with the linearity assumption, and it's important to realize what we mean when we say a linear model versus a linear relationship. A linear relationship between variables is very typically what we think. It's this line, as x increases, y increases linearly, or as x increases, y decreases linearly. So this term linear, when you think line, that tends to refer to linear relationships between variables. Now, this is important because the linear model that we tend to use in regression and what our assumption is based on is slightly different from this linear relationship. What's fascinating about this and really, really useful is that you can actually fit a nonlinear relationship using a linear model. So, for example, y equals the quadratic formula and y equals some regression equation using the natural log of x. Neither of these would give a linear fit. The quadratic formula would obviously give a quadratic curve fit, and this would give a natural log fit or inverse exponential. Both of these are considered linear models. Now, these are not linear relationships, but they are linear models. So how is this possible? Well, first we have to understand, what do we mean when we're talking about linearity and the linearity assumption? The linearity assumption makes the assumption that we have a linear model, not a linear relationship, and that's kind of the core component. A linear model means statistically that the model is a linear combination of the predictors. And by linear combination, what we mean is that y is the sum of some constant times the x values, where the x values are independent variables and the c value is a constant. You'll note that this sum goes from 1 to p, that is from 1 to the number of independent variables or predictors that we have in the model. And these c's are just our betas normally. Thankfully, this formula of the linear combination, which is what we need to have a linear model, makes no mention of x in terms of what needs to be linear. X could be any variable. It could be the natural log of x, it could be whatever. As long as the c's are constant values, then this counts as a linear regression. Because of this, nonlinear patterns in the residuals, we talked about some curves and stuff that can occur with the residuals, can actually be solved by introducing a nonlinear function of x as a predictor in our linear model. So we look at the nonlinear relationship with the linear model by including something like x squared, which we demonstrated on the previous slide. This is super handy because what it means is nonlinearity, as opposed to being some mystical problem that we have difficulty fixing, is actually more analogous to missing an important predictor. So if we have a nonlinear relationship in our residuals, this is just missing the predictor that accounts for that nonlinear relationship. So let's say our residuals had kind of this U-shaped. What this would tell us is, well, we're missing a squared predictor, so we need to add in x squared as an additional predictor to account for that nonlinear shape. This is so handy, and it's something that many students don't understand, is that actually we can fit a ton of different models with a ton of cool and complicated curves using a linear model. Because of this flexibility, we'll find out later in the course that these linear regressions, which can fit a whole ton of curves and have a whole ton of options available, are often called general linear models, or GLM for short. We'll come back to this term later in the course because there is a couple more caveats to the term general linear model that goes just beyond our basic regression. But actually, we're getting to the chapter. I think maybe in even the next lecture series, we will visit this term again. There are such things as nonlinear regressions. So you might think, oh my gosh, well, if I can model curves with a quote unquote linear model, then there's nothing I can't do. Well, actually, there are some different equations that you don't have access to with just linear models. So there are nonlinear regression models that we have to have access to those types of relationships. They are much less common than you think. That they are out there, but again, this linear model can handle virtually, well, I won't say any situation. It can handle a very, very, very wide variety of situations, much wider and broader than you would think if you just thought about a single line as the limitation of linear models. Though these nonlinear regressions can be used, they are really beyond the scope of the course. We will kind of talk about some concepts that are related to these, but we won't even talk about the fact that that connects to nonlinear regression models. So we'll give you some tools that if you end up taking a more advanced course that talks about them, will allow you to understand them a little bit better and how they relate to what we're doing in this class, but we won't actually go into depth in that discussion. One of the reasons that we don't particularly talk about them is they apply by different sets of rules. So because of the lack of linearity among the parameters, and recall that it's not a lack of linearity in the relationship, this is a lack of linearity in those C's, those constants that are required for the linear combination, many of our techniques have to change. So we'd have to use different parameter estimation techniques, different model fit. We can't use things like R squared or the percentage of variance explained anymore. We'd have to change our significance testing, and there's a lot more things that get manipulated because we don't have access to those traditional tools and those traditional model fit statistics. So we also have the non-constant variance assumption. If we don't have constant variance, and recall in regression we call it homoskedasticity, that's constant variance, and heteroskedasticity, that's not constant variance. So if we have heteroskedasticity, that's the bad one, we may be able to actually use a better statistical model to account for the change in variance. Now this is probably the best approach. When we can. So what you'll find is that when we use fancier models, a lot of our limitation is, do we even know about the fancier model? And do we have the skills to implement fancier statistical models? There's no shame in saying, hey, I have no idea how to implement a statistical model that accounts for variance increasing and then flattening out and then decreasing at the end of my residual plot, making this weird hexagon shape. So don't worry too much about a case if you would say I don't know the model, but sometimes if you do know the models, say you took the nonparametric regression class or nonparametric statistics course and learned about a couple nonparametric methods that could account for this, then maybe you could use a better statistical model that doesn't require a constant variance assumption. Now I will say that actually most statistics models do require constant variance, and we may talk about that later in a different chapter. If we don't have access to a different model, sometimes we can use a transformation to stabilize the variance, and very strangely, these are called variance stabilizing transformations. Good shots initially to try out are taking the log and the square root of the variable to see if after we take the log and rerun the regression, if our residuals look a lot better and have a variance, if they have equal variance in the residuals, that homoskedasticity that we're looking for. One procedure that really helps us when choosing transformations, and we're going to spend some time talking about this when we get to the transformations component, is the box-Cox procedure. This one's pretty famous, and it is a really, really, really useful tool that helps us, especially when we're first getting started and we don't know all of the possible transformations we could pick and are having trouble picking which would be the best one. For our non-normality, we actually have similar approaches. The approach, though, differs based on if we know the error distribution or not. If we do know how the errors are distributed, we can use a statistical method that actually accounts for that type of distribution. So for instance, we've made the assumption for our model that the errors are normally distributed. However, there are statistics, and statisticians have made models that assume the errors are distributed according to different distributions. Now, we talked about how what we are doing is called a general linear model. When we allow the errors to be distributed in any way other than normal, as well as some other things, that moves us into the world of generalized linear models, which is a broader class of statistics that we won't go much in depth on. We will focus on general linear models in this course. But just so you know, these are available, these better statistical models. So for instance, if we assume the errors are binomially distributed, then we may have a logistic regression. If we assume that the errors are Poisson distributed, we may have a count regression, and so on. Now, it's important to realize that in generalized linear models, in addition to having different error terms, there are also different things that happen within the model itself. So we don't just change the error terms, but we do have access to different error terms that we can use. And actually, I think we could just change the error terms. We'd run into some other issues, though. So be aware that it's not quite this straightforward, but it is relatively straightforward, especially once you get the hang of implementing it in a software like R. You simply tell R the error distribution, and it applies all the rest of the changes I just mentioned for you, so that you can simply say the errors are distributed according to a binomial distribution, and the model fits appropriately. So very, very handy, very, very convenient and useful if you're familiar with implementing these types of models. And again, it's very nice because if my errors are not normally distributed, if I know how they are distributed, I simply implement the better model and I don't have to worry about the assumption of normality. If I'm not familiar with these approaches, sometimes I can use a transformation to help, just like the heteroscedasticity issue. So if I have a non-normality issue, sometimes a transformation can help to fix the lack of normality in error terms to become more normal. So we talked about transformations in two processes. We talked about them for homoscedasticity and normality when we're trying to get homoscedasticity and normality in our residuals. Now, transformations can fix both, and it can be good because what can happen is both of these assumptions can break at the same time, and if they do both break, sometimes you can apply a single, simple transformation, and both of them get immediately fixed. The counter to that convenience is that sometimes if only one is broken, if you apply the transformation, it will break the other one. So let's say normality, I'm having a normality issue, but my homogeneity of variance is fine. If I apply a transformation, sometimes what can happen is I fix my normality issue, but now my homogeneity of variance is all messed up. So we have to be careful when we're implementing transformations that the transformation fixes the problem that I'm interested in fixing and doesn't break anything else. To make sure that we are careful about this, every single time we implement a transformation, we have to recheck all of the assumptions, not just the one that we're trying to fix. So if my normality is broken and I'm implementing a transformation using that approach to fix normality, and I run my new model, I don't just check that normality was fixed. I have to recheck all of the assumptions to make sure that I didn't break any assumptions while I was fixing normality, because normality may work, but hey, maybe now my homogeneity of variance is broken. So we're looking for transformations not just that fix one assumption, but we're looking for transformations such that with the transformed data, all of our assumptions have been properly fixed. One other issue that we run into is outliers, and I want you to be careful because there's a lot of articles and a lot of practice documents that talk about deleting outliers. With outliers, we do not delete outliers just because they don't fit a pattern in our data. In fact, I was recently reviewing a journal article for a top-tier journal in a particular field where the author of the article, I was reviewing this article for some statistical help, and the author decided to any outlier that was above a certain amount of standard deviations, they just removed from the data set because they didn't like that particular data. It wasn't demonstrating the point that they wanted to make. We do not do this. If data don't fit your theory, you don't just get to delete them. So that is not something that we do. And this is really, really, really important to understand. You do not just get to delete outliers because they are outliers. One of the best ways that I know to look at outliers, especially extreme outliers, if they're real outliers, is to look at them for areas of further investigation. So when I see a data point that's way different than all the rest of the data points, I'm going to check into that data point and see why is it so different. And there's many reasons it could be. Now, I mentioned that we don't just delete outliers, but it's important to note that if I'm investigating the outlier and it turns out that the data was simply mistyped, so somebody kind of fat fingered the number in there, or the data was on a different scale than everything else was on, or any of these systematic issues, it is absolutely acceptable to correct it and simply make a note that there was a correction. When I say don't delete outliers, what I mean is this outlier wasn't a data entry error or anything like that. This outlier was an actual observed value. You don't just get to remove that observed value because you don't like it. So if the source is an error, do correct that error and make a note. Now, if the source isn't an error, what then do we actually do? So one useful thing is to look for different patterns among the outliers. So what I'm going to do is I'm going to look at the outlier and I'm going to see, is something weird going on? So let's say I'm looking at the average weights of individuals. And I'm taking, let's say I'm standing in a, oh gosh, how do I do that? Okay, yes, let's say I'm standing in at the door of a football stadium, at the door that the players run out. And as players are running out onto the field, getting all hyped up for the game, I stop them at the door and I say, how much do you weigh? And I don't let them run out on the field until they tell me how much they weigh. And so I get all of these weights, and then in the middle of all of these weights, I find somebody who weighs 120 pounds. So I've got weights that range, say, from 180 to 300 pounds, those big old linemen. And then I have one data value that is 120 pounds with just nowhere else's weight anywhere near that. And I'm kind of like, what on earth is going on here? And so on further investigation, what I find is that this individual is the only female football player in the league who's playing in the boys' league. And this individual weighs 120 pounds or something like that. Now, in that case, what I may see is that this individual represents a different pattern. That is a pattern of male-females impact on weight than maybe what I'm trying to study in that particular case. So what I can do is account for this pattern methodologically. So what I may say in my study is that in my study, I'm only going to look at the weights of male football players. Note that I am not excluding the outlier because it's an outlier. What I am doing is I'm making a note and excluding the entire pattern. That is, I'm excluding all females who appear in my study. So if there was a female who weighed 285 pounds who was in the study, I would also exclude that individual, because what I would say is methodologically, this subgroup is not what I'm trying to investigate with my particular research. So this is absolutely okay to do. If I can identify the pattern, I can methodologically account for it by excluding that particular whatever pattern led to that. You'll see sometimes this happens with let's say like student intelligence scores. I'm trying to assess the importance of a teacher's pedagogy, the lessons that they're using on student intelligence scores. And what you may find is that I have a student in there who has a severe intellectual disability. Instead of trying to make the claim that, because students with intellectual disabilities respond to different teaching pedagogies and stimuli, what I may choose to do, instead of trying to make the claim that the student is, like, instead of including the student, and instead of just deleting the student as an outlier, I may say I'm not going to include students with intellectual disabilities in my study. Now, in many research studies, you will see this as as researchers define the sample that they're interested in. You'll see things like, we're only studying males in this age range, or I'm only studying individuals without intellectual disabilities, or sometimes I'm only studying individuals with intellectual disabilities. Incidentally, finding these patterns are a great way in which you can identify future studies that need to be conducted. So I could look at a study and say, oh my gosh, this individual has an intellectual disability. It would be really interesting to see how pedagogy impacts individuals with intellectual disabilities. So for my current study, I'm going to make a methodological decision about that particular pattern, intellectual disability, and say that in my current study, I'm not looking at individuals with intellectual disabilities, but in a future study, I'm only looking at individuals with intellectual disabilities to study that pattern. Now, we just talked about exclusion methodologically. You can also include statistically. So what we could do, recall my football player example, is that we could add another variable to account for the sex of the individual who's playing. So we could say, okay, we've got a variable that says male and female, and so we account for that new pattern statistically. And again, this works when we can identify the pattern. So we have to be able to identify what separates this person who weighs 120 pounds. And if we can't find that, we can't account for it statistically, of course. But if we can identify that, we can include statistical variables that account for it. Now, what happens if there isn't a pattern? I look at this person who weighs 120 pounds. I don't really see anything that separates them. I mean, they don't play any weird positions. They don't have any intellectual disabilities. They're not, they're not a girl on a boys football team. Nothing's going on. It's just an outlier. What do we do? Well, first, when we just have outliers in our data, it's not an error, and I can't find a pattern that maybe needs to be excluded methodologically. And again, you always make a note when you do this. So in all of the examples I mentioned writing in my study that I'm only going to look at males, or I'm only going to look at individuals without intellectual disabilities. So if there is not a pattern and I can't find that, then what I really need to check on is how much does this outlier actually matter? We spoke briefly about influence, but the influence of the outlier is a great thing to check on if I have an outlier and I can't find a pattern associated with it and it's not a data entry error. The reason we check on this is because it may not actually matter. If it doesn't really influence the results, then maybe there's no harm in leaving it in. And I might just mention, hey, this point seems to be an outlier, but doesn't affect the results. So no real harm in leaving it in. If it does influence the results, we can use some robust estimation procedures that de-emphasize the impact of outliers. So we use a different estimation procedure that systematically, it doesn't remove the outlier, it just doesn't account. The outlier isn't as influential in these different procedures. Actually, many of our non-parametric statistics are fantastic in the presence of outliers because they study the medians instead of the means and perform median comparisons instead of mean comparisons. As we've talked about, I think, at the beginning of this course, and as you know from your previous statistics courses, medians are much less influenced by outliers than means are. So when we implement a non-parametric statistic, the outlier simply doesn't have the impact on the median that it does on the mean. I don't know that we talked about that in this class, but I'm sure you talked about it in your previous statistics courses. Sometimes when we do transformations, that can also help with outliers. You'll see things like log transformations that drastically reduce the size of many outliers. And in some cases, this is a really important thing to take into account, is that sometimes we just have to transform our data. There's some famous examples where transformations are extremely effective in dealing with outliers, but we do want to be careful with the transformation approach. Finally, and I will just say it one more time, we do not just get to change data values because we want to. If it isn't an error, if this outlier isn't somebody's error somehow, then we don't just get to change it or correct it. Again, if it is an error, we were doing inches and you gave me millimeters or something like that, then you can absolutely change it. But if it's not an error, you don't just get to correct it. All right, so a few other problems, and then we will be done with this video. The next video we'll talk about transformations. But some other problems that come up are these correlated errors, a lack of independence. What do we do when we don't have independence? Well, there are many statistical models that allow for what we call a correlated error structure or a lack of independence. Some examples you've already seen are t-test, a paired samples t-test you've already seen, I'm sure. Maybe the repeated measures ANOVA you may have seen in Math 116. Mixed models, HLM, hierarchical linear modeling, GEE, the generalized estimating equations, GMM, the generalized method of moments, and time series are all more advanced models that are very commonly used to address this, that you have not seen before, it's safe to say, but are all common methods to implement. I've actually done work with all these, so all of these are very, very good methods that you can use in their particular place and time. Another problem that can come up is the omission of important predictors. So we discussed in our checking of diagnostics and checking out those residuals how we can look at that, looking at a plot of the potential predictor to be included versus the residuals. It's a bit clunky, but it is one way if I've got a series of predictors and I'm concerned that one maybe should have been included in the model, that I can check on it. And frankly, the fix, if you've omitted an important predictor, is to include the important predictor. Now, when we include multiple independent variables in the model, we get into a statistical analysis called a multiple regression, which will be the focus of the last half of this course. And it's in multiple regression that our options really, really explode as we're allowed to include multiple different predictors. But the solution, again, if you've omitted important predictors, is relatively straightforward. Just include the predictor of interest. Now, if you don't have access to the predictor of interest, that's kind of an interesting case. Now, it's a shade of gray, just like all these assumptions are. You know, if you slightly violate normality, you can probably keep going. If you have major violations, you probably need to correct it. The same thing is true here. In your predictors. If the predictor is only slightly related to the outcome and slightly related to the independent variable, then you may not really need to worry about it. Just make a note that you don't have it in there. But if it's extremely related to the outcome and extremely related to the independent variable and how those things relate, then it's going to be very, very difficult to make the argument that your analysis is meaningful and your conclusions and interpretations are valid if that predictor isn't included in the model. So it's important to weigh kind of the contribution and the importance of the predictor that's omitted, if you know an important predictor has been omitted, when you're considering if you can go forward with your conclusions and if those conclusions can still be interpreted appropriately and applied appropriately. In the next video of this lecture, we will talk about transformations in the wonderful world of transformations, what's involved with transforming data, and a few of the details of how we go about doing it.